so now it's time for the punchline. Okay, we've been building up how to deal with the time evolution operator. We introduced a iterative solution to the equation of motion for the time evolution operator, the full one. Then we realized we could write that as a series or a summation, the Dyson series, with the idea that maybe we can cut it off after some term and that we would have an approximate solution. But we don't want to do that for the whole Hamiltonian, right? We want to do that. We want to consider the Hamiltonian to be able to be broken into two pieces. And our derivation so far makes no claims whatsoever about the nature of these two pieces, just that it can be done. Once you do that, then you find out that there's another picture you can introduce called the interaction picture, right? The interaction picture uses the U-naught Hamiltonian, the time evolution operator for the H-naught Hamiltonian to transform, for example, the H-primed Hamiltonian into what we call the interaction picture. Then what we were able to do, we used that intermediately. We're going to come away from that, and we don't really need the interaction picture after. The key insight that we gained was that we would be able to write the state vector in the Schrodinger picture, sort of our home base, if you will, as a product of U0 Ui times the initial I, right? And of course, this is because this is the psi of I of t, the interaction picture of state vector as a function of time. This involves it. I didn't put the times in there because it reproduces what we've already done. And so what we recognize, the key is that we can write the time evolution operator as the product of U0 times Ui. We know what U0, we potentially know what U0 is. It's the U for the H0 Hamiltonian. And Ui is the time evolution operator for the interaction picture version of H primed. And so what we're going to do is we're going to use the most common application of this is where we know H0. We may even have it be time independent. And then we assume that the H primed term is small. And what we of course mean by that is the energy change that you have by including H primed is much smaller than the characteristic energy scales of H0. If you want to think of it, H0 as a bunch of energy levels, then the change in energy would get from H primed is much less than what the energy difference between two levels, for example. Then what we're going to do is keep U0 intact and then expand perturbatively in a series and then truncate, so perturbatively, the Ui part. All right, so let's work that out. We're not going to make any assumptions at this point. We're just simply going to do the math straight. And then, of course, at the end, we're going to make all these approximations. So everything we've done up to now is still completely 100% exact. All right, so what we want to do is use the fact that we have the time evolution operator is this product of U0, TT0, and Ui, TT0. And what we're going to do is we're going to leave U0 as is, and we're going to write the Dyson series for Ui. We need a lot of space for this. And I'm trying to stay away from the edge. I know that I have a tendency to get too close to the edge. Sounds very risky, doesn't it? All right, so we're going to write down a few series terms, and you'll see why in a minute. All right, and this is going to look like the sum on n equals 1 to infinity minus I over h bar to the n. That's that factor that's always on in front. And then our sequence of integrals, these nested, folded integrals. D tau n, and then dot, 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 down to the last one, tau 2, d tau 1. Okay, and then here's what we get when we plug in h primed I. Remember, this is simply using the formal solution that we had by the time using the time time-ordered exponential operator. Now we're just writing that out explicitly for ui here. We have h primed I of tau n, right? And I'm going to put a little extra term maybe just to make it really clear. Tau n minus 1, the next one, all the way down to h primed I tau 1. All right, and what is h primed I again? Let's remind ourselves. So h primed I of t is equal to u naught t naught h primed u naught t naught. All right, so it's this transformation from what you might think of as the Schrodinger picture to the interaction picture, right? Where the t part for this, the t dependence of the h primed is coming from some intrinsic time dependence, like the fact that it's a field that's oscillating, for example. All right, so now what we're going to do is now what's the problem with this equation? There's nothing wrong with it, but we don't really want to keep it in this interaction picture, right? So what we're going to do is there's a really amazing thing that you can notice what's happening. If you look from right to left, which is how things work, right? It's going to operate to the right. So first, you will operate on your state vector with h primed I. So like the thing that's in the h primed Hamiltonian. Let's say it's the hammer, whatever it is that you're doing to change the system, the plucking. All right, you pluck it at t1 or tau 1, then you're going to pluck it at tau 2, then tau 3, and tau 4, and you're sort of adding up the effects of all of this as you do all of these nested integrals. All right, let's see if we can figure out how to convert this back into a set of equations, or back into an integral that involves the Schrodinger picture operators. Right? Those are the ones that are more intuitive for us, probably. Okay, so here's what I'm going to do. I need to develop a little bit of a manipulation that we can do. So let's consider some term that you're likely to find in the middle here, like the last two terms. H primed I of tau n times h primed I of tau n minus 1. All right, what we want to figure out is, what is this? What is this? Okay, so what we know it is, we can simply use the definition of what an interaction picture operator is and just plug it back in. All right, so what we're going to have is and we just have to follow the rules. T naught is always going to be the other parameter in U naught. But the T parameter will change. Here it's going to be tau n, here it's going to be tau n minus 1. So for the first term, h primed I tau n, it's going to be U naught tau n T naught. Okay, then h primed I tau n, and then U naught tau n T naught. This is one of those cases where it'd been nice if I should have probably written it all the way around here. But whatever, I'll do it this way and hopefully it makes sense. Then we're going to multiply this by the next bit. All right, well, what's the next bit? The next bit is U naught. So times tau n minus 1 T naught h primed tau n minus 1. And then U naught tau n minus 1 T naught. That's the first two terms of this. And let's look at what happens at the intersection of these two terms. So at the intersection, we have U naught tau n T naught, and we have U dagger tau n minus 1 T naught. All right, and we want to figure out what that is and how we can simplify that. All right, so one way to think about this is to think about what does the U operator do. So if this is T naught, U naught, or any U, evolves a system, let's say, to the point T. All right? And then you might ask, well, what does u naught dagger do? Well, if u naught times u naught dagger gets you 1, then one way to think about what u naught is it takes us from t naught to t, and u dagger takes us from t back to t naught. That's why doing this and then this has the net effect of doing nothing, right? It's the identity because it's a unitary operator. Okay, so let's think about what's happening. The first one is going to take us from t naught to tau n minus 1. Now here's the other thing that you can do with time evolution operators, is that they add, essentially, if you make a product of them, right? They're these exponentials. And you know, if you make an exponential like e to the a times e to the b, it would be e to the a plus b. Now you have to be careful about that. That's only true when you have commutative algebra. When you have non-commutative algebra, things are a little bit more complicated. All right, so let's look at what a normal time evolution operator does. Is if I do t naught, then I expect to evolve from t naught to t, right? There's no reason I couldn't have first stopped here, somewhere in between, and then gotten to t. How would I do that? Well, I would just imagine making t smaller, and then I would just do the rest of it afterwards, okay? So that means the first time evolution, instead of going all the way to t, I go to some other time. Let's call it t1. I start from t naught. To go the rest of the way, I just have to go from t naught, or the initial time will now be t1, to t. So you can break the time evolution into any number of steps you want, or that would be convenient. So here's what we're going to do for our combination operator here. So the combination operator that we have, that's the product of these operators, is u naught tau n t naught times u naught dagger tau n minus 1 t naught. So what we're going to do is we're going to take this one, which goes all the way to tau n. This one only goes back from tau n to t naught. We're just going to break this one into 2 pieces, right? The 2 pieces we're going to do, we're going to break this just like we did here into u naught tau n minus 1. That's the last bit after we get to tau n. And then we have u naught tau n minus 1 t naught. The starting point all the way up to tau n minus 1. Then we have the second term, u naught dagger tau n minus 1 t naught. And what do we see? Something pretty amazing. Look what happens to this term here. It's u dagger. U dagger is 1. All right, so we convert every one of these pairs into this pair of operators that goes first from the initial time up to the step just before. And in fact, it's u dagger, so it goes backwards. And this one goes from tau at t0 up to tau n. So really what we're doing is the difference between these two. All right, so it would look a little bit like this. This one goes to the back from the, not all the way here, but here. Right, so from here back. So what we end up with is the net time evolution between these two. And what are these times? These are the times when the interaction, whatever h primed is, has occurred. Okay, so when you recognize this remarkable feature, you can rewrite all the pairs of terms. First, you convert them back to the Schrodinger picture. So you explicitly include the u naught operators to convert from the interaction picture back to the Schrodinger picture. Then every single pair of these h primes is going to have a u naught u dagger with a slight time difference, which we can then replace with u naught from the earlier time to the later time. Remember that we know that they're ordered like that because we have this time-ordered exponential operator. So when we do that, we have this remarkably simple formula, and it's easily interpreted right away. right? So let's write this down. 1 plus the sum minus I over h bar to the n, and then all of our integrals. And I just want to make sure I choose the right number of integrals. All right. So what I'm going to do is I'm going to bring it down here, all right, because I need the width. These are very long. These equations end up being very long. All right, so then we have T naught up to T, d tau n, T naught up to tau n, d tau n minus 1, all right, all the way down to T naught up to tau 2, d tau 1. Okay. Now we still will have the last h prime, the last u naught dagger, which you'll see we can get rid of that in a minute. So we're going to leave that in. Maybe I'll make it yellow, so make it orange, just to highlight that we still have to deal with it. But all the rest follow this pattern, right? So we'll have h primed tau n. Then we're going to have u naught tau n minus 1. We just derived that over here. And we keep going. The next one is going to be h primed tau n minus 1, then u naught tau n minus 1, tau n minus 2, and dot, 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 all the way down to the last sort of 3 terms, which I'll write as u naught tau 2, tau 1, h primed, I was doing it a different color, h primed tau 2, nope, tau 1. Right. In a minute, we're going to interpret this, and we're going to have a very, very, very simple way of thinking about it. That's why it makes my error more egregious. Because I should know that. What's going on here? All right, so, and then the last one, right, is tau 1, T naught. All right, so if you notice what's happening is this, you can almost read this like a story. System, this is the U is going to do something, right? It's going to operate on the state vector, or it's going to operate on the density operator. Whatever it's going to do, it's going to operate on a thing that tells what system state we have. The first thing that happens is it just evolves all by itself. It evolves by itself, meaning in the absence of whatever h primed is, which of course, let's think about it as the light or the pulse or the hammer or the whatever you do. So it evolves all by itself, what we might use in the jargon, field free, and then bang, we do something to it at the point in time tau 1. Okay, but then we let it evolve again, as it would, without the extra perturbation or the extra interaction for another period of time, tau 1 to tau 2. Then it's not drawn here, but there'll be another one, h primed tau 2, and so on. So you go from the evolution under h naught, application of h prime, evolution under h naught, application of h prime, and so on. As many times, and of course, if you do it exactly, an infinite number of times. And then you change when they happen, and you add it all up. Now you're keeping the order. Now what about the last term? The last term is just hanging out there, kind of like a scab. How do we deal with that? Well, we notice that there's another term that we had kind of ignored before. But here's the cool thing about the term. The term doesn't depend on any of those taus, of course. So we can bring it into the integral if we want. Usually you want to bring things out of the integral. Here you can bring it into the integral. Well, what happens when we bring this term into the integral? Look what's going to happen. We have another one of these convenient tricks of the U dagger thing. So we bring it in, we have u naught t naught, u naught dagger, tau n t naught. So we'll do the same thing. We'll break this one up into evolution from tau naught, T naught up to tau n, and then from tau n to t. So the last bit will be tau n to t. Now we have to read everything backwards, or from right to left. U naught, of course. Then we have U naught, tau n, T naught. This is U naught dagger. We have the same thing. Tau n, T naught. That's 1. And so we just have now this one term that replaces this when we bring in the U naught into all of this. Now that means it's also going to be multiplying the 1 here. All right, so what I'm going to do, because it deserves being written down completely, is I will find us some space and I will write this final equation because this is one of the good ones. Okay, so let's write the final expression for the time evolution operator. Keeping in mind, this is exact. We have not made any approximations yet. All right, so we have U naught, T naught, because of the 1 here, and then we're bringing this in, plus the sum right, and then we have all of our integrals. Okay, and then we have our last term. Probably I don't have enough room, so I'll write it over here. So we have U naught T tau n H primed tau n U naught tau n minus 1 H primed tau n minus 1. All right. All the way down to the last term, which is U naught tau 2 tau 1 H prime tau 1 U naught tau 1 T naught. All right, and that is literally an exact expression for the time evolution operator when you have a time-dependent Hamiltonian, whatever it is. The only stipulation is that we can separate the Hamiltonian into 2 pieces, which is very general and not something that you need to worry about. All right, and that we got here by going through the interaction picture, but you notice there's no more interaction picture here. It was a tool we used to get to this point. We understand this as field free, field on, field free, field on, field free, field on. Okay? And of course, now where does the approximation come? Well, the approximation comes by assuming that there will be scenarios or situations where we don't need all these terms. All right? We may, in fact, have a field that's weak enough that a very low order term will be the only thing that we need to deal with. Because if you look at what's really happening here, is you have multiple interactions with the field. It's essentially like we have powers of the field. Right? That's what you would normally do in a power expansion. And if you have something that's small and you start raising it to a higher and higher power, the net effect gets smaller and smaller and smaller. Okay? So what we're doing here is we're setting up what's called time-dependent perturbation theory. And there is going to be quite a bit of thought and guidance about how we choose which parameters or which elements of this sum we keep, which ones we ignore, and when it's legal to do all this stuff. Just briefly, the most simple rule of thumb from the point of view of a spectroscopy course is that when you are trying to model something like linear spectroscopy, like infrared absorption, UV absorption, things like that, absorption spectroscopy, that will be first order in the field for the time evolution operator. Now you might say, why is that? I expect that signal to depend on the intensity of the light. Well, remember, we're only looking at the time evolution operator. What's going to be happening is we're going to be using the time evolution operator to compute our wave function at various times, starting with some initial condition, like being in the ground state, if it's the wave function. Or if we use this to do the transformation of the density operator, then we might say, assuming that we're in a Boltzmann distribution, a thermal distribution, but even then, if we're talking about like electronic or visible or vibrational spectroscopy, basically we're in the ground state there too. All right, and then we're going to use the time evolution operator to transform the density operator to a later time, just like we already have proven all those formal equations by now. When we go to actually calculate something that's related to spectroscopy, for example, the expectation value of the dipole operator, which is going to be the thing that leads us to linear spectroscopy, it's a little bit more complicated than that. We need to worry about something called the time correlation function of the dipole operator. Nevertheless, we're going to be a kind of squaring this, right? And since we're going to be kind of squaring this, if it looks like we're using one field, then we're going to be really using the power of the second power of that field. And so that's why you see something that looks like an intensity when you do that calculation or that experiment. But it is one field interaction with the material. And we're going to be talking very much about how to think of that intuitively and mechanically. What happens when a field is interacting with a molecule? All right, and so that would be an example. So linear spectroscopy is so-called linear, particularly because it is linear in the field. Now, it's probably the people who talk about it this way think about it as being linear in the intensity. Okay. Unfortunately, there are other experiments that are linear intensity that are certainly not linear in the physics. Fluorescence is a good example. Fluorescence appears linear. If you're doing a fluorescence experiment, and you double the power of your excitation light, you will double the number of molecules you excite, and you will double the fluorescence. It's very straightforward. So it makes you think that fluorescence is also linear. It is linear in your job as the fluorescence spectrometer person exciting the molecules, but actually the world is conspiring to cause emission, and that extra step makes fluorescence nonlinear. So we will derive all that. We will explain and understand fluorescence actually as a four-wave mixing process, as a nonlinear optics process, but one where you don't have any control over that second kind of interaction, the stimulating interaction. That's actually done spontaneously by fluctuations of the electromagnetic vacuum. Similar in Raman effect. Anything that has spontaneous emission has something like that going on. Absorption is a little easier to understand. The field you apply generates a polarization material. The polarization of the material radiates light because it's a time-dependent dipole moment, and you end up with emitted light that's out of phase with the driving light, and you see net absorption. So first order in the field will be things like linear absorption spectroscopy. Second order in the field is going to turn out to be things like second harmonic generation, or some frequency generation spectroscopy, which is really very common technique nowadays. It would also explain something like difference frequency generation, which is how we make infrared light, for example. Right? So that would be a second order interaction with the excitation, making a polarization material which generates light, and then you detect it. A three-field interaction, 1, 2, 3, is going to be anything that's like a pump probe experiment. You excite, but then you detect. Two field interactions makes an excited state. We'll understand that as we go. And then you can probe what happens after you've made that excited state. If the two field interactions occur simultaneously, you might have what we would call a traditional pump probe, transient absorption. It's the same thing. If you split apart in time those first two interactions and change their time as a function, and change the delay between them, for example, with pulses, you could measure something that we now call two-dimensional spectroscopy or multi-dimensional spectroscopy, which is a kind of pump probe experiment with multiple time delays. This would also explain NMR, two-dimensional NMR experiments like COSY, TOXY, NOSY experiments. So those are experiments that rely on higher interactions, higher order interactions with the field. And as you will see, that's important because it teaches you more things about the molecule or the material than you could have learned with a single interaction. You can learn about dynamics. You can learn about the origin of dephasing. Why is it that when I look at one molecule in one solvent and I put the same molecule in another solvent, the spectral widths aren't the same? Why is that? There's nothing here that should tell us why that would be. Now we're going to figure out why all that is, and we're going to see how you can use that information to learn about chemistry. Because you have multiple interactions, you can start a chemical reaction. You can cause a bond to break, for example, and then you can follow that process as a function of time. You can also change the frequencies of these fields. You don't just have to think of everything as being in the time domain. You could apply one frequency and then another frequency and then another frequency and then look for a signal at yet another frequency. And what we'll do is we'll develop the full formalism that allows you to predict what are all the possible signals that you could measure given a set of input fields that you've put in there. So that means we will have one formalism to explain everything. Linear absorption, Raman spectroscopy, coherent Raman scattering, spontaneous Raman, stimulated Raman, pump probe, transient absorption, 2D IR, 2D electronic spectroscopy, combinations of all these things, right? And NMR, of course. Now I sound like a bit of a fool. I say, and the analog and the NMR analogs of all these things. Well, of course, it was the other way around, right? The NMR was first. We copied them, right? So then we'll have automatically an understanding of how you can get to NMR. So any kind of optical spectroscopy that you can do, barring a few examples like that are important but are not in, obviously not included in this, you can understand what this formalism. So we're first going to do, we just worked out perturbation theory. We're going to do a few examples, of course, and look at what happens if you have a linear field, and you'll see things, and we can add resonance, so you can see that there'll be a resonance criteria. We'll learn about the linear susceptibility and the Kramers-Kronig relationship, very important things that relate, for example, absorption and dispersion. And then we're going to get into a slightly more theoretical concept of the equation of motion for the density operator, which we already talked about, is the Liouville equation. We can evolve then the density operator using the perturbed approximate Hamiltonian time evolution operator. And then we will also develop the formalism of the so-called optical response functions of arbitrary orders. That'll allow us to understand, at least existentially, maybe not the molecular interpretation, but why do we get signals? What kind of information do they tell us? In the history of this field of optical spectroscopy, beyond just linear absorption and imagine eating photons, there were times when things weren't so clear. It seemed like, oh, I did a much fancier experiment with many pulses and time delays. Surely I'm going to get more information than somebody who just looked at the spontaneous Raman of emission of something. Well, it turns out if you're looking at the same correlation function, even though you're using a fancy laser versus a simple one, sometimes the information content is exactly the same, even though it's much harder to get in one way versus the other. So now we have a perspective. We're looking back, and we have had people come before us, people like Charles Mukamal, who really helped to put everything in this single view reference frame. And that allows you to see, right, I have this sequence of pulses at these frequencies and this timing. These are the experiments that will come out of this, from this combination. And so fortunately, we have a way of a taxonomy of light matter interactions, at least at the level where perturbation theory works. Now, since we have this formalism for perturbation theory, and we just finished doing a whole bunch of stuff with exact two-level system dynamics, of course, we're going to check the two. And we're going to see that there are some predictions that you would make from perturbation theory that are absurd. And you can show that they're absurd if you look at what the exact solutions are. And that'll teach us some very deep things about the fundamental limitations of perturbation theory, when it will be applicable and when it won't be. And that's very important because so many things in science, just from the simplest example of like Hooke's law, I always explain this when I'm teaching about Hooke's law. The force is the negative force, right, is kx. This is a slope of k. The more you pull it out, the bigger the force gets. And it's a straight line if you use Hooke's law. But of course, if you go into the real world and get a spring, this is not how it works. If you pull a spring a little more, eventually it's really, really, really hard to pull the spring because you've undone all the coils. And now you're just pulling on a piece of metal. Right? And there's going to be some tensile strength to that metal. And all of a sudden, the force to pull will be enormous. But if you're strong enough, and if you have a machine that can do this, eventually you pull so hard, it breaks somewhere, right? And then, of course, the force goes down. Once I have two pieces of a spring, I can separate them however I like. This is a real spring. This is Hooke's law, all right? So many things that we learn in science are a very low order Taylor series expansion of a much more complicated thing. So you can live your life at the linear limit, the linear approximation, and that's fine. But if you have stronger lasers or higher temperatures or other things that allow you to see higher order correlations, you're going to start to be able to pick out the deviations from these simple models. Sure enough, what happens to the spring if you pull it too far? Of course, it becomes not a harmonic oscillator because the force is not linear anymore. If you integrate it, you'll get the potential, and it won't be quadratic. It'll have other terms in it. Well, we know what happens when we add other terms to the potential. We get anharmonicity, which means we won't have a single vibrational frequency. We'll have a more complicated motion that might go woo, woo, woo. And we take the Fourier transform of that. We're going to see all kinds of harmonics, which is why a flute and a clarinet sound different. They can both play the same note. There'll be some frequency will be the same. But a flute basically has one frequency. It's like a harmonic oscillator for music. And a clarinet's going to have all kinds of harmonics, which is why it has that sort of buzzy sound. All right, so spectroscopy is the same. You can live your life in the linear response range, right? And then you can do FTIR and UV-Vis and use it for measurements, and that's fine. But if you want to push the information content that you can get from molecular systems, you need to be able to see beyond. You need to see beyond the leading terms of the Taylor series. Now you can do that if you use higher order optical spectroscopy. Right? And that is where, of course, many people are doing research in this area now. But it's not even unusual anymore. It's becoming much more common to do nonlinear spectroscopy, ultrafast spectroscopy, spectroscopy with multiple frequencies if you don't like the time domain version of it. And so the goal of this class is to show you how that all works, but also to show you the molecular connections. Because if we don't make molecular connections, then it's just a bunch of equations, right? That's not going to do any good. Once you do this, you don't have to do this again, unless you want to calculate things. What we want to do is we want to take these equations, mix them with some relatively straightforward go-to chemical models, and then lock that away, and then try to see how we can find what we might call intuition about other physical systems that you haven't studied before or that aren't the model, right? And that's what very many people do now, and especially with the new technology of the spectroscopy. And of course, there's also people who do computations and theoretical simulations. And so we will talk about how can you do molecular simulations to get information that will allow you to compute, for example, the optical response function, right? And there's really neat ways of doing that now. And I will go over how you do that. And maybe we'll even include that in a problem set that you can do yourself.